All right, so in this chapter, we'll study magnetic fields. What we'll see is, you guys have probably all seen magnets and played with magnets. Magnets will produce magnetic fields. Okay. They'll produce magnetic fields like this. Magnetic fields are denoted by B. Okay. And they're vector fields. What do we mean by vector field? So these field lines, you see the magnetic field lines start at the North Pole and end at the South Pole. Okay, the field lines tell you at this point the magnetic field is tangent to the field line. Okay. Okay. Now let me remind you. Well, okay, let's do it right here. Okay. In one of the previous chapters, you learned that we had electric fields, and to detect an electric field, what did you need to detect an electric field? I'm sorry?
I don't want to be wrong.
Why not?
Another electric field?
And you need a charged particle.
I was going to say that or a charged particle.
And there you go. See, you were 50% right. Okay. If you place a charged particle, it'll feel a force like that. Okay. You place a negative charge, the force is in that direction. Okay. So you need a charged particle to detect an electric field. So what you learn in this chapter is you will need a moving charged particle, okay, to detect a magnetic field. So the force, so this is the main this is the punchline on the chapter. The force on a moving charged particle is given by that. Okay. So let's look at this equation. If the charge is 0, if the particle is not charged, the force will be 0. If the velocity is 0, the force will be 0. So if you have a charged particle that is at rest, you cannot detect the magnetic field. Okay? So what you need is a moving charged particle to detect a magnetic field. A particle at rest can detect an electric field. Okay? All right, so this is what this chapter is about. We'll learn what are producing magnetic fields. Magnets produce magnetic fields. Okay? And what you need is a moving charged particle to detect a magnetic field. Okay? In the next chapter, you'll learn that it's not really magnets that produce magnetic fields. It's moving charged particles that produce magnetic fields. These produce magnetic fields. So here's a beautiful symmetry. Moving charged particles produce magnetic fields, and that's what you need to detect a magnetic field. But you already saw this. Charged particles produce electric fields, and to detect electric fields, you need a charge. So whatever it is that produces it is what you need to detect it. Okay? All right, so you will learn some of these topics: magnetic fields and forces on charged particles. Okay, that's the main punchline. Magnetic forces on a current-carrying conductor. If you have a conductor carrying current, there's a whole bunch of moving charges, and if you place it in a magnetic field, it'll feel a force. So we'll introduce magnetic fields here in this chapter, and then the forces the fields exert on moving charges. Okay. And in the next chapter, we'll study that moving charges produce magnetic fields. Okay. And then we'll talk about electromagnetic induction and so on. Okay. So these will be things are not varying with time, and here things will vary with time. Okay. Again, here are Maxwell's equations that summarize all electromagnetic phenomena. In the next chapter, we'll learn moving charges. This is current density and electric current density. So this is the cause, this is the effect. Moving charges produce magnetic fields. This equation also tells you that time varying electric fields produce magnetic fields. Okay? But we'll come to that later. Okay. So the second thing you'll learn is magnetic fields are denoted by B. To detect a magnetic field, to sense a magnetic field, you need a moving charge. Okay. A moving charge feels a force in the presence of a magnetic field. Okay. All right, so in this room, there's a magnetic field, the Earth's magnetic field. And to detect this magnetic field, all you need to do is take a charged particle and throw it. And if it gets deflected, then there's a magnetic field in this room. Okay. What this equation tells you is when will this force be zero? So let me just write this. Under what conditions will this be zero? Let's say Q is non-zero and V is non-zero. Can this still be zero? When will it be zero?
There's no magnetic field at all.
Okay, so none of those terms are zero. Can this still be zero?
If they're parallel.
Very good. So when V is parallel to B or V is anti-parallel to B. So the cross product of parallel and anti-parallel vectors are zero. Okay. The cross product of these two vectors are zero, and the cross product of these two vectors are zero. Okay, so the only time that charged particle won't be deflected is if you throw it parallel to the magnetic field. Okay. All right, so if in a room there's a magnetic field, you throw a charged particle and let's say it's not deflected, well, either the field is zero or you happen to throw it parallel to the field or anti-parallel to the field. So you grab the particle again and throw it again in a different direction. And if it's still not deflected, then there's no magnetic field. Okay. All right, here are magnets. Here are two magnets. Like poles repel each other. Okay. And unlike poles attract each other. So, okay. All magnets come with two poles. Okay. And there are magnets of various shapes. Here's a horseshoe magnet, bar magnet, and so on. Okay. Here's what happens. When you break a magnet, you don't destroy its magnetism. What you get is two magnets. Okay. So this will be a north pole and a south pole. You keep doing it. You break this, what do you get? I'm sorry?
Another magnet.
You get two more magnets. Every time you break a magnet, you got two more magnets. Okay? Essentially, this will go till the atomic level. So in a simplistic picture, the atoms are magnetic. Okay? So the story is a little more complicated than that, but okay. Unlike electric charges, magnetic poles have always been observed in pairs. So magnetic monopoles are postulated, but by some theory, magnetic monopoles are these guys. So just like charges, you see a positive charge and a negative charge separately, but we've never seen a magnetic pole by itself. Okay? Some theories do postulate them. So here's what we're going to study. We're going to get a bar magnet, and the bar magnet produces magnetic fields all around it. How far does this field go? To infinity. Okay. And obviously the strength decreases the further out you are. Okay. And you see the field lines start at the North Pole and they end at the South Pole. Okay. North Pole, like poles repel like poles. So when you have a field line like that, the field is tangent to the field line with the North Pole pointing in the direction of the field line. Okay. And here's how you use a compass to, we use a compass to tell north. So we'll come to that in a second. Okay. So magnetic fields exist around magnetic materials. Moving charged particles. Okay, so this is something we'll study in the next couple of chapters. Moving charged particles and time varying electric fields are sources of magnetic fields. So what this line is saying is this equation. Moving charged particles is current density, and time varying electric fields produce magnetic fields. This is the cause, this is the effect. Magnetic field lines are denoted by B. They are a vector field. What does that mean?
And direction.
That is, at every location, you drive. At this location, there is the field is like that, and so on. Okay, they're a vector field. Okay. They can be time dependent. For now, we are just going to study time independent fields. Okay. Magnetic fields at a point can be defined in terms of the force they exert on a moving charged particles. Okay, so at the field at this location can be defined by the force it exerts on a moving charged particle. Okay. And here is the force. So let's make sure we understand this. It's a cross product. The magnetic force exerted by a magnetic field on a charged particle, Q is QV cross B. So it's the cross product of the velocity vector times the magnetic field. And again, if the particle is uncharged, the force is zero. If the particle is at rest, the force is zero. And of course, if the magnetic field is zero, then it's zero. Okay. Also, if the two vectors are parallel to each other, then the force is zero. Okay. So let's see this. Okay. There's the velocity vector. There's the magnetic field vector. The force is perpendicular to the plane containing these two guys. Okay. And you would use your right hand rule. Okay. So velocity, if you turn from velocity to the magnetic field, if you turn a screw in that direction, the screw would move in that direction. Okay. The direction in which the screw moves as you turn from V to B, that's the direction of the force. Okay. So you want to use that. That's the most convenient because, so let's say this is the velocity vector and there is the magnetic field. You turn from V to B, the screw would move that way. That's the direction of the force. Okay, let's say V is like this, and that's B. V to B, the screw would move up. Okay, that's the direction of the force. Okay. So the force is always perpendicular to the direction of motion. See, okay. So it turns out that, let's say if you want to speed up an object, let's say this is a car moving in this direction. If you want to speed it up, what do you have to do? You have to push in the same direction as the motion, or you need to have a force in the direction of the motion. Here, the magnetic force is applying a push perpendicular to the direction of motion. Okay. So if a car is moving in this direction and you apply a force like that, all you can do is deflect it. Its speed does not change. Okay, so you cannot accelerate a particle using a magnetic field. Okay, you can't pump energy into it. Okay, you can only deflect it. Okay. Well, you're accelerating it, but you're giving it centripetal acceleration. And all right. So you can't speed up a particle using a magnetic field. Okay. So there's the force on the charged particle. The force is 0 on a charged particle at rest, and so on. Yep. Okay, again, here's the right-hand rule. If the velocity is like that and the magnetic field like this, the force is perpendicular to the plane containing these two vectors. There's the force. Okay, so what you do is if the particle is a negative charged particle, you calculate the direction of the force as if you have a positive charged particle, and if it's a negative charged particle, the force is in the opposite direction. Okay, you still use the right hand rule, or you could use your left hand for negative charged particles, but it's best to use the right hand. Figure it out as if it was a positive charged particle, the direction of the force, and then if it's a negative charged particle, then the force is in the opposite direction. If the charge is negative, the force is in the opposite direction of that of a positive charge. Electric forces on charged particle is in the same direction as the field, whereas the magnetic force is perpendicular direction. Since the magnetic force is perpendicular to the direction of motion of the charged particle, it can do no work on the particle and hence cannot change its energy. Yeah. So you can't increase the energy of a particle, of a charged particle, by placing it in a magnetic field. All right, now we'll look at the units. So again, you have to have an equation to get the units. So B is force divided by QV. Force is Newton, charge is, Q is charge, V is meters per second. So the units for B are Newton per Coulomb meter second. Coulombs per second is ampere. Coulombs per second is ampere. Okay. So the units are Newton, ampere, meter. And this combination of units is called a Tesla, after Mr. Tesla. Yep. A Tesla is a large field. The Earth's magnetic field happens to be about 10 to the minus 4 Tesla. Yeah. It's actually half of that. Okay. So it turns out that planetary fields are of the order of 10,000 Tesla, so we give this a new name called a Gauss. Okay, so 10 to the minus 4 Tesla is 1 Gauss. The Tesla is the SI unit for magnetic fields. Okay, it's just that it's that's a very large unit. Yep. Mm-hmm.
So what is 1 Tesla? Why was it defined that way?
1 Tesla, that's the magnetic field you need for 1 Coulomb of charge moving at 1 meter per second to have a force of 1 Newton. Okay. 1 Coulomb of charge is a large charge. Do you remember how much charge does a thundercloud have? I'm sorry? That's electric field, you remember. So a large thundercloud has about 10 coulombs of charge. A coulomb of charge is very large. Yeah. So okay, so here are the fields with, I guess. So strong lab magnet is only about 30 Tesla. If some of you guys went to the microkelvin lab at UF, you saw that those guys had 14 Tesla magnetic fields. A medical MRI machine has about 1.45 Tesla. The stronger the field, the higher the resolution image, okay, and the higher the cost of the MRI. So a cheap MRI probably has a 1 Tesla magnetic field, and an expensive MRI has 3 Tesla magnetic field. Yeah. So the field inside your brains, when your neurons are firing, those produce a field of about 10 to the minus 13 Tesla. Here's the Earth's magnetic field. So the Earth's magnetic field on the surface of the Earth is typically about a fraction of a Gauss. Okay? So this shows you in here the magnetic field is 0.3 Gauss and so on. Okay, so here you'll have to imagine things in 3 dimensions. Okay. So again, you'll have to use your right-hand rule and stuff like that. So to indicate the direction of the field, if the field is coming out of the sheet, okay, so here, imagine an arrow. Okay, remember the magnetic field is a vector field. Okay. So if the field is coming out of the page, then you're looking at the arrowhead and you're seeing a point. And if the field is going into the page, you're looking at the tail of the arrow and you're looking at crosses. Yeah? So that's how we indicate magnetic fields coming out of the sheet and magnetic fields going into the sheet. Okay, you saw that the force on a charged particle is that. A moving charged particle is that. Now, if you have a wire that is not carrying any current, if there's no current, then there's no moving charged particles, and you place it in a magnetic field, there won't be any force on it. This magnetic field is into the sheet of the paper. Now, if you pass a current in this wire, a current is, you can imagine, well, it's really electrons. In a metal wire, it's electrons moving in the opposite direction. But imagine a bunch of positive charges moving in this direction. Okay? And so a bunch of charges moving in that direction, the magnetic field is into the sheet. V cross B would be a force in that direction. Okay? So V cross B would be a force in that direction. Okay, so here's V and there's B. The force would be in that direction. Each charge would feel a force in that direction, and there's a whole bunch of charges moving in that wire. Each charge is feeling a force in that direction. The force on the wire will be the sum of the forces on all the charges. Okay, so this is very useful, and we'll see this in a second. Okay, so you pass a current in a wire, put it in the presence of a magnetic field, and suddenly it feels a force. You can use this for many things. All right, you pass the current in the opposite direction, the force is in this direction. And so this force is, that's the force on a single charge, and that's the number of free charges per unit volume, and that's the volume area of cross-section of the wire times the length of the wire. That's the volume of the wire. So that's how many charges are moving. That's the force on each charge, and the net force on the wire is the sum of all that. And all that amounts to, so the force is I, the current in the wire, times the length of the wire. That's in the magnetic field, and this is given a vector sign. The length vector is pointing in the direction of the current. So the force on a current carrying conductor is I L cross B. If I is 0, there's no charges moving and the force is 0. If the current is parallel to the magnetic field, there's no force on it. Okay? And so on. All right. So here's a bent wire. You guys are all calculus experts. So this was a formula for L being straight. Well, if you have a bent wire, all you do is break it up into little straight pieces. Okay, so the force on this element is I ds cross B. B is in that direction, ds cross B. If you turn the screw in this way, the force is coming out, df is coming out. Okay, so the force on each element will be coming out of the page, and you can calculate the force. So that's df. Okay. And then you can sum it all up. All right, we're going to do that. So let's say the wire is like this. Okay. What we're going to do is place it in a uniform field. So the total force on this piece of wire is I ds cross B. All right, B is going to be constant, so that can come out. The current is constant. So I ds. So all we're doing is summing all these elements of the wire. And cross B. Now look at this. Sum of all these little arrows is this vector. So all you do is, if you have a bent wire, the force on it is you draw a vector from the starting point of the wire to the end point of the wire. And the net force is I times that vector crossed with B. So what we are saying is the force in a uniform magnetic field, this is true only in a uniform magnetic field. In a uniform magnetic field, the force on this wire is the same as the force on this wire, as long as they're carrying the same current, is the force the same as the force on this wire, and so on.
So that means path independent?
Very good. It's shape independent, as long as they have the same endpoints. In a uniform magnetic field. What is the force on a closed loop? Hmm? Okay. All these vectors add up to a zero vector. The net force on a closed loop in the presence of a constant magnetic field is zero. Okay? The net force on a closed loop is zero. So, on a closed loop, there's no effect? No. So this is the most important lesson you'll learn in this chapter. Okay. Do you guys know who does the most work in the world?
My mom.
Your mom. Well, she does 10% of the work. 90% of the work is done by electric motors in the world. Your mom only does 10% of the work. Okay, so now we'll learn how electric motors work. Okay, so let's make sure we understand this. Okay, I know I'm recording this, but all right, so we'll pass a current through this, like this, and the magnetic field is, okay, well, let's follow this diagram. Okay, the magnetic field is like that, and we have a loop of wire, and we'll pass a current like this. Okay, so on this guy, the force on this guy, I cross B, so the magnetic field is like that. I cross B will be a force outwards. The force on this guy will be coming out of the page. Everybody understand that? How about on this guy? B is parallel to it. So the force on these two guys is 0. The force on this guy is 0. The force on this guy is 0. How about on this guy? The force is I cross B, the force will be in the opposite direction. Okay. All right, we just said if the magnetic field is uniform, the net force on a closed loop is 0. That means this force, if this is 10 newtons, that's 10 newtons in that direction. Okay. The forces are equal and opposite. But the torque is not 0. What these two forces will do is, so if you have a magnetic field in this direction, the force on this guy is in that direction, the force on this guy is in that direction. What they'll do is they'll turn it. That's how all motors work. You take a piece of wire, put it in the presence of a magnetic field, and if you pass a current through this loop, it'll turn. You convert electrical energy into mechanical energy. That's how 90% of the work is done in the world. And then for the rest of the 10% of the work, you go to Nolan's mom.
There's systems where the net force in the closed system or surface isn't 0.
I'm sorry?
Can you go back to the slide before that? Are there net forces on a closed loop where it's not equal to 0?
Okay, how would you make that non-zero?
The forces would have to be not equal to each other.
Right, so make it a non-uniform magnetic field.
So would it still torque?
Yeah, it would still have torque, but it would also move.
Oh,
Okay. All right, so very important. So in a uniform field, a closed loop there'll be a torque acting on a closed loop, okay? And the maximum torque is when the loop is in the plane of the magnetic field. Okay. All right, the maximum torque is I, the current in the loop, A times B. A times B. That is the area of the loop. The torque is larger the current, larger the area of the loop, times the magnetic field. Stronger the magnetic field, greater the torque. Okay, so what we'll do is the following. So here's the magnetic field, and so here's this diagram is simplified, and here's how you remember it. Okay. Here's the direction of the magnetic field, direction of the current. Use your right hand, point your fingers in the direction of the current, right hand, not left hand. Point your fingers in the direction of the current. That is the direction in which the area vector is pointing. Your thumb is the direction in which the area vector is pointing. And if you put this current carrying loop in a magnetic field, the area vector will turn towards the magnetic field. That's the direction of the torque. That's what the torque is doing. It's turning this area vector towards the magnetic field. So that's the direction in which it will spin. Okay, so all this is in a uniform field. Okay, so this guy is called the magnetic moment. Here's again. So let's say I put a magnet like this in the presence of a magnetic field. What will happen? The North Pole feels a force in this direction, the South Pole feels a force in this direction. Okay, the magnetic field turns the magnet, it lines it up towards the magnetic field. It turns the magnet like that. You see this current carrying loop, it's doing the same thing. It's turning the loop in that direction. So a current carrying loop is behaving like a magnet. Okay, a current carrying loop behaves like a magnet, and the magnet points in the direction of your thumb. The strength of this magnet, the magnetic moment, is N, the number of loops, times the current, times the area of the loop. This is huge. This is called an electromagnet. Why is it good? As engineers, you should be jumping up and down. Why is it good?
To create a magnet, like a magnet.
This is a magnet. You get tired of it, you turn it off. Shut the current off. You want to make it stronger, have more loops. You can pass a higher current. This is great. You go buy a magnet like this, you buy a permanent magnet, you get tired of it, you can't turn it off. Okay? So this is an electromagnet. Okay? You can change its strength as you need it. Okay? You can turn it on and off. You switch the direction of the current, you flip the poles. Okay? This is very versatile. Okay?
So it still has a magnetic field even when you turn it off or no? Or
No. See, if current is zero, then the magnetic moment is zero.
Oh, because the current's going through, okay.
Yeah. So this is called an electromagnet. Okay? The torque is the magnetic moment crossed with the magnetic field. Okay, so if I place a magnetic field in that direction, what the magnetic field will do is turn this torque toward the magnetic field. Okay, now your brain is cranking, and you're going to do all kinds of applications. Okay, and by the way, so the potential energy, it's like this thing has potential energy. Okay, when you drop it, it turns into kinetic energy. So let's say you have a magnet, you have an electromagnet, you have a loop like this. Okay, carrying a current. So there's the moment. And if the magnetic field is pointing in this direction, what does the magnetic field do? So think of this as north and south pole. It's turning the magnet in that direction. So it gains kinetic energy. Okay? And so the potential energy got converted to kinetic energy. Okay, that's its potential energy. Okay, we'll come back to this in a second. We'll come back to all that in a second. So here's the most important application as far as you guys are concerned. Okay, so here's how electric motors work. And let's make sure we understand this. So here, all electric motors have permanent magnets that's producing a magnetic field like this. What do electric motors do?
Turn electrical energy into mechanical energy?
Very good, my friend Eli. What would I do without you, my friend? Okay. All right. So here's a magnetic field. Okay, that's the magnetic field produced by that magnet. Okay, here's a loop of wire. I'm going to pass a current through this loop like this. So here's my loop of wire, which is behaving like a magnet. What did that magnetic field do? When I pass a current, that's when this behaves like a magnet. If I don't pass a current, it's just a loop of wire. Boring, useless. Okay, I pass a current. Here's a magnet. It turns the loop like that. Okay. Now what I'm going to do is, I'm going to be mean. See, the current was like this, remember? Right when it gets there, now I'm going to switch the direction of the current. So now it's become a magnet like this. Switch the current again. Keep turning it. That's how the motor works. And the electric motor converts electrical energy to mechanical energy with over 90% efficiency. You get into your car and try and convert heat into mechanical energy, and what are you getting? 20% efficiency, 30% on the best day. On a regular day, you're getting 20%. Okay. So this device, okay, so if you connect it this way, the brush is this way, that's when you're switching the current at the right time. Okay. So these are amazing things. Electric motors convert electrical energy into mechanical energy. Okay. All right.